Good morning, everyone. Today we're looking at Unit 2, Lesson 2, Polynomial Functions and Function Notation. So you all should have seen functions in 3M or 3U, whichever one you took. So we're just going to kind of quickly review what is a function and how do we tell if an equation is in fact a function. So first of all, let's talk about a relation because a relation is part of a function. So what is a relation? Example, linear quadratic relations we looked at in the last note. So a relation is an identical pattern or a relationship between two variables or two sets of numbers. So think about in a linear relation or a quadratic relation, right? The x and the y have some kind of relationship going on within the equation, right? Y is equal to x being multiplied by something and something being added to x, okay? So there's a relationship that happens there. So what is a function? Well, a function is any relation in which every input, so remember your inputs are your x values, has only one output, which are your y values. So every x can only have one y mapped to it. So here's some examples of relations and functions. They can be represented in a variety of ways. So we can have an ordered pair, or what we would call coordinates if we were looking at a graph. So we have 0, 1, 1, 3, 2, 5, and 3, 7. That is showing that 0 and 1 have some type of relation, 1 and 3 have some type of relation, and so on. We can show it with an equation, so either a linear equation, a quadratic equation, or we have an exponential equation there. It can also be shown with arrows or a mapping diagram. I should have another bracket there. Okay, where it's showing the input and then an arrow is pointing to the output that relates to that input. We can show it with a table of values relating the x's and y's. We can put those x and y's on a graph and show it with a graph. So you have an exponential graph here, a circle, and then just kind of a trend graph or line, if you will, there. So we'll talk about which of those are functions in a minute. But if we are looking at the graph of a function, how can we tell if it is in fact a function? And it has to pass what we call a vertical line test. So a vertical line test is if a vertical line crosses the graph only once, the relation is a function. So you can see there's a direct correlation between these two things. Every x value can only have one y value. If we were to draw a vertical line, we're basically ensuring that there's only one y value for that given x value. So if we look at this line here, can we tell if it's a function? If I draw a vertical line, right, all the way down, it's only going to cross that graph once. Okay, and I can draw that vertical line anywhere. Same is true of a parabola. No matter where I draw a vertical line, it's only going to cross the graph once. So since the vertical line only crosses each graph once, each one is considered a function. Every input, or x value, has only one output, or y value. Okay, so if we come up and if we look at some of these relations and function examples we have up here, let's look at this ordered pair. We have to look and think, okay, do my x values only have one y value? So if I look at 0 to start, does it have another y value? Well, no, it only has 1. If I look at 1, does it have another y value besides just 3? Just 3, okay? Same is true of 2, and same is true of 3. So we could say this is a function. All of these equations will represent functions, and if we put them on a graph, you could see that they would pass the vertical line test. Let's look at these arrows, okay? Something to think about here. We have an input, 5, has an output of 7. 8 also has an output of 7, okay? But 5 still only has one output, so only one output. 2 of our inputs have the same output, but they are still only having one output for each of them, so this is a function. Now we'll look at this next one. This next one is where the problem kind of lies. Here's my input, and now this input has two outputs. Has two y's, doesn't have only one, so we would say that this is not a function. All right, and we could look at our table of values as well. If you look at our table of values, our -2 x value, okay, is going to have a y value of -2. But it also has a y value of +2. If you look down here, you have -2 again. And so again, there's two outputs here, so this is not a function. All of our graphs, we can assess if they're functions or not by doing that vertical line test. So if I draw a vertical line here, it only crosses the graph once, so we would say this is a function. My circle, hopefully we can see that no matter where I draw a vertical line, I'm going to cross it 2 times, so not a function. And this graph as well, even though it's a kind of a zigzag line, no matter where I draw a vertical line, I'm only going to cross the graph once. So this is also a function. All right, so we are going to continue to look at some other characteristics of functions, but let's talk about, if we had a line or if we had a parabola, how might we make it so it wasn't a function? Because right now it is a function based on the vertical line test. So how would you change the graph so that they were not functions? So if I took that parabola and I turned it on its side, okay? So we turn the parabola on its side. As you can see, once I've turned the parabola on its side, if I try to do that vertical line test again, it's going to cross at 2 points, right? So my x value there is going to have 2 y values for, it looks like my x value is 5, so it's not a function now. Okay, so this graph is not a function since the vertical line crosses the graph more than once. Every input has 2 output values, except for which one? So where could I draw a vertical line that would only cross the graph once? Well, it looks like if I stayed anywhere, if I was here, it's going to cross twice. Here, it's going to cross twice. Okay, where can I draw my vertical line so that it's only going to cross once? And there's only one point that isn't symmetrical to another point, and it's this point right here. So that is my vertex when the parabola is upright. So which one only has one output is going to be our vertex. So that's just a little bit about functions and remembering that vertical line test and that every input only has one output. Let's now look at function notation and evaluating functions for a given value. So a function written in a way that uses all x's for the variable is denoted f of x. It can be read f of x. Just highlight this. We read that as f of x. Think about the output of f for input x. So we're basically saying we're going to substitute in, we're going to input an x value into our function and figure out what's the output going to be. So if our function example that we have here is f of x equals 2x squared plus 3x minus 1, we're going to evaluate this function for some input. So when we're evaluating a function, a number, term, or function will replace the x in the function. So it's going to replace the x. So if we have f of 2, we could write this as f of 2 is equal to 2, and then anywhere there was an x, we're going to replace it with a 2. And then we just start simplifying. So 2 squared is 4, 4 times 2 is 8, 3 times 2 is 6, minus 1. So f of 2 equals 8 plus 6 minus 1 is 13. So therefore, the output of f for x equals 2 is 13, or we could say it's a coordinate, right, where 2 is your x and 13 is your y, okay? Other than just subbing in a number, we can actually substitute in an expression or a term. So that's what we're going to look at in this next part. Functions can be combined using numerical operations. So find g of 3 minus h of 2. I'm going to pause it, and I'd like you to figure out what is g of 3, do that part, and then figure out what is h of 2, and then we'll come back together and subtract those two, okay? Okay, so here's the solution. If we substitute in the 3 into our g function, so g of 3 is going to equal 13, h of 2 is going to equal 8, and then if we subtract those values, so if we take g of 3 minus h of 2, we'll just take the answers we got for each of those and subtract, and we'll have 13 minus 8. Or we could set it up as one big equation. So we have g of 3, so we could set that up as, we know that the function of g is 4x. In place of my x, I'm going to substitute in a 3 plus 1. And we're taking that g of x, and we're subtracting h of x. So then I could subtract my h of x function and substitute in the x they want me to for h, which is a 2. So we can have it all in one equation as opposed to calculating each of them and then subtracting. Either way is fine. So 4 times 3 plus 1 is 13. 3 times 2 is 6, plus 2 is 8. So 13 minus 8 is 5. So you can see same either strategy. Whichever one you choose will work. Okay, so let's set up the next one and then pause it, and you guys can finish that as well. So we're going to set up this next one as the entire expression that we have here. So we have 3 times, okay, we're going to have 3 times something in here, minus 45. Okay, so we're going to substitute in h for 6 into my bracket. So we're going to have 3, and then in my bracket we're going to have this h of 6. So I'm going to substitute in h, the function of h, and plug in a 6 for my input, or x value. And then just start simplifying. So 3 times 6 is 18. 18 plus 2 is 20. 3 times 20 is 60. 60 minus 45 is 15. Okay, so lots of way that we can kind of combine functions. There's one more that we're going to look at for the note today. So a composition of functions is basically where we have one function embedded in another function, and we have to solve. So let's just remember, because it was on the other page, our functions were g of x equals 4x plus 1, and h of x equals 3x plus 2. Okay, so this is asking us to do h of g of x. And just keep the colors like that so we can see where we're inputting the g's into the h's. So our outermost function is h. So I'm going to start by just writing h, but I'm going to leave a space here for where was our x, because we're going to substitute something in for our x, right? It's saying that we're going to take this g of x, we're going to take g of x, and we are going to substitute it into our bracket. And we're going to substitute in g of x and then simplify and see what we get. So let's just write that in the next step. So h times g of x is going to equal 3, and then in place of that bracket I'm going to substitute in my g of x, which was 4x plus 1, and then we have that plus 2 that's also on our h of x. So now we'll just start simplifying. I'm going to leave everything in the same color now. So we'll have to distribute our 3 into our bracket. So 3 times 4x is 12x. 3 times 1 is 3, plus 2. So we could say h of g of x equals 12x plus 5. Now if you were asked to determine this combined function, or this composition of functions, for a given input, for an actual number, so h of g of 2, let's say, we now could substitute the 2 into the simplified function that we have made by the composition here. So we could say h of g of 2 is going to equal 12 times 2 plus 5, which equals 24 plus 5 is 29. All right, so function notation, substituting those inputs in to a function and determining what output we're going to get for the function. Well, that's it for today.